Thank you. Welcome everyone to today's workshop Wednesday session. Today we'll be having Harith Bakhrani taking us over system design and how to scale your system up to serving 1 million users. The last workshop Wednesday, we had Kenneth Kabiru taking us over anonymizing production data, and unfortunately, that video isn't on our YouTube due to some technical hitches that we had, but the slides are available to share upon request. Uh, for this work session, we'll be having Harith present, and towards the end, having Q&A. You can post your questions here on the call if you're present here, or on the YouTube live stream chat, and we'll get to them towards the end. Harith, take it away.
All right. Thank you for having me. So let's begin. Let me start sharing my screen. And yeah. So right. So something about me. My name is Harith Bakhrani, and I'm a DevOps engineer for 4 years now. On my DevOps journey, I've been working with various products, and I've been hosting, creating architecture on the cloud, and enabling the organizations to ship them quicker, efficiently using the CI/CD pipelines. Um, yeah, so one of my interest in is system designs, and that's what I'll be talking to you today. So how this is just an introductory system to the system design. How can we serve millions of requests with ease and without, with quickly as well to the customers? So what we'll be covering today is we'll start off with the single server setup. So we'll see uh, how traditionally people used to host their on a single server, and how it has changed today. Then we'll go on to scaling, how we can scale our systems to accommodate more users, and various two types of scaling. And the third thing we'll be talking about is how we can take out state from our servers to be able to scale better, as we'll see. And the fourth topic today will be of caching to basically serve data with speed. Then, as we move on, last two topics will be content delivery network. So we talk about CDN network. So CDN is basically will be serving static files. So it's a cache for static files, and then we'll go to asynchronous and CPU heavy tasks. So we'll look at how we can uh, decouple the synchronous tasks and those that rely heavily on CPU as well. All right. So to begin, we'll look at our single server setup. So how people used to traditionally set it up. So traditionally set up the servers, and it unfortunately it holds true till this day. So what used to happen is that traditionally, or even today, people have this one server where it's the single source of truth. Everything, all the requests come into this single server, and it's responsible for everything. So the data is being stored here. It's serving the requests. The sessions are being stored here. So it's everything basically. The front end, the back end, if there are any other services. And the issues with having just one server is that, well, basically we can have an overload. So even if you have 16 CPUs, and you can have 64 gigabytes of RAM, at one point it will get overloaded if you are serving traffic to like millions of users. And as concurrent traffic gets higher and higher, our server will start running out of resources. So we'll run out of RAM, we might run out of CPU, and we'll no longer be able to respond to requests in a timely manner, and we'll experience lagging in sending the responses. Another thing we can look into, like another issue, is that single point of failure. So if our this one server was supposed to go down, our entire business would be taken out of of service, and we no longer be able to like serve our customers, and businesses can go into loss this way. And some of the reasons that our server can go down is like one of them is power outage, the other one is that application can crash, and well, there can be anything else as well. Uh, so two main reasons to have a single server, like why people used to have a single server in a traditional setup when cloud was not available, is that the equipment was really expensive. Until today, equipment is really expensive. If you want to set up 3 4 servers, uh, you need lots of money, and for a startup, this is not like startups don't have this much money, and it also requires highly skilled personnel. So you want to set up servers so that they serve traffic, all of them they serve the traffic, so that one server goes down, the others continue working. And you also need a load balance between on the server. So you need highly skilled personnel to be able to like set all this networking up, and you need to hire very knowledgeable people, and this also is really costly. Uh, well, today we are really fortunate. We live in the cloud era. So cloud era has changed a lot of things. It has really become easier and cheaper to host our application, to make it available to to the entire world. Anyone can come in and start. We can start serving the requests. Mm, we can basically, you can think of it like, I can go to the cloud today. I can get a virtual machine at 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 the spot. The RAM, I can choose the RAM, I can choose the CPU. I can set up everything, the networking and everything, just in one in matter of clicks. As we will see, like how it has really impacted the system design, how we are now actually preparing for the cloud, and how it has made really easy to create this really good system architecture. All right, so this brings us to our next topic, which is scaling. So moving beyond one server, so this, it applies to like the traditional way, like having physical servers, but with cloud, it's really easier today. So first we look at the vertical scaling. Vertical scaling refers to adding resources to our existing server. So if our server was we are running with 4 GB RAM and 2 CPU, we upgraded it to run with 8 GB and 4 CPU. And if that wasn't sufficient enough as well, we can also upgrade it to 16 GB RAM and 8 CPU. Again, we do have issues. We still have a single point of failure. We have just one server. If it goes down, our entire business is down. And another thing is that this, even like, we'll run out of resources at the end. How much can we expand our one server? It's limited. So this brings us to our next type of scaling, which is horizontal scaling. And horizontal scaling means to add additional identical servers to serve the traffic. So we can have multiple servers over here. And it really has to do with adding redundancy in the architecture. So we are adding same server, serving the same application. So if it's serving the front end or serving the back end, it's serving the same, all of them will be serving the same traffic. Now, how do they serve the same traffic basically? Uh, we use a load balancer. So if there's a load balancer, and load balancer basically distributes the traffic between the different servers we have. So first, load balancers has different algorithms by which it routes the traffic to different servers. So the first one is a resource, like not the first. The common ones are resource-based and round-robin. There are many others, but the most common one is the resource-based. So resource-based load balancer distributes load based on what resources each server has available at the time. So if we are running out of resources on server 1, it will serve the traffic on server 2 or server 3, and it will like let the server 1 cool down. The other algorithm is round robin, which basically sends requests on cyclical basis. So the first request will go to server 1, the second will go to server 2, the third one will go to server 3, and it will come back to server 1, server 2, server 3. So it's just a cyclical basis. The load balancer is not aware if the server 1 can handle the traffic or not. It will just send it. All right. So there is a catch though over here. We have been talking about single point of failure. And well, having a load balancer, single load balancer is, we are still having single point of failure. We'll need to have like 2 or 3 load balancers so that one, if one goes out of service, the two continue working and serving our traffic. Yeah, so we don't need to worry. Cloud basically takes care of all of this. If we, for example, if on GCP, if you were to create a load balancer, GCP makes sure that our load balancers are highly available, and you know, like if one of them goes down, the others will continue working. So this is really nice thing about cloud. All right. So the horizontal scaling, the challenges that we face over here with horizontal scaling is that, let's say if we are storing some state, right? So if we have a database, if we are having also a database server in in all of these servers over here, what happens is that if I come in and the load balancer takes me to server 3, I sign up. It creates my user ID and my username. The second time I come, it would it may send my request to a different server, right? So it may send it to server 1, and server 1 will reply, "Hey, there's no username with the name of Harith J." So basically, this is one of the challenge that we face with the horizontal scaling, and we'll see how to overcome this challenge shortly. Uh, the second challenge you can face as well is that when we said we can create our architecture on the cloud, is basically we are creating servers which can scale up or down depending on our traffic use case. So if our traffic is high, we might have 3 or 5 or even 10 servers serving the traffic. And when our server gets low, you know, it may cool down to having only 2 servers, server 1 and server 2. So taking a look at this scenario over here, uh, if I come in and I sign up and my request goes to server 3, server 3 will save this up. But when the server scale down due to like there is no traffic or there's very low traffic coming in and server 1 and server 2 are enough, this server 3 will be taken away, right? So there is no more server 3. So my sign up information, my information that I used to sign up is basically gone, just wiped out. And no matter how many times I come through the load balancers, I'll never be able to reach server 3 because it's no more there. It's just scaled down and the system is taken away. And to be able to uh, like to be able to overcome this challenge, we need to go stateless. We need to make our server stateless. Now, what does it mean? Going stateless means that the servers, our application servers, those are that are serving the traffic, do not store any users' data. They do only one purpose, and their purpose is to serve requests. Data is stored in other servers. So basically, as you can see over here, these 3 servers which we had earlier on, which are serving the traffic, are now basically communicating with a database server, with a single database server. And we need a single database because, as we said, we can't have multiple databases because we can't scale horizontally. There are many other ways to scale the database. We will look at them later. But this one is not for this purpose. We have the three servers communicating with an external database service. So there are three kinds of stats that our application usually stores in the application server. So our application server store basically. One of them is general information, which is user information, and this kind of information is stored on the database. So we have already seen that we have taken out the database outside of our application servers, and it's now just storing the state or the general information our application needs. The second one, the second one is the objects. These are images, videos, PDFs, and any other objects which, like, it's not good to store them in a PostgreSQL database or any other database. And we will see where we can store this. The third one are sessions. So this basically refers to the sessions of like when I as a user I log in, the server will remember me through the use of sessions, right? So these are three main kinds of stats that are usually stored in app servers. Uh, and where can we store them? So we just saw that the general information, we all know that we can store them in an external database service. But what about the objects? Well, GCP and also AWS and all the other clouds that are out there uh, have the storage facility. So Google Cloud has Google Cloud Storage. AWS has a service known as S3. And this service is basically, their purpose is to store these large objects, the videos, the images, PDFs, etc. And what about sessions? So for sessions, we can use an external service like Redis, or we can also use another kind of database that someone needs. Yeah, basically, a NoSQL database works for the sessions. So what does our overall architecture look like so far? So basically, a client comes in, and the first one to get our client is the application load balancer. The load balancer will then route the traffic to the actual servers. And these servers, keep in mind, these are auto-scaling web servers, so they can grow and shrink horizontally. And we also have, these servers are also communicating with the database, which could be our PostgreSQL database. It could be our NoSQL database, any kind of database, which stores the general information about our applications. We then have the cloud storage, where we store our images, videos, etc. And then finally, we have our Redis server. For now, we are storing sessions in it, right? So caching. How how do we serve data with speed? Like, caching basically allows us to serve data really quickly to our customers. It's a temporary data storage server, so it's just temporary. We don't use it to store uh, permanent data in it. We store temporary data, but it serves data really quickly. So for example, Redis, we can Redis stores the data in it uses random access memory to store its data, because random access memory is really quick. It's really quick to get data from the random access memory than it is to read from an SSD drive or SSD drive, right? So, but as we all know, that random access memory is just temporary data storage. Once the server restarts, all the data is gone. How does cache work? basically the client will communicate to the web server. The web server will try to read data from the cache. If it's not found, it will read data from our database server. So once it reads the data from our database server, it will store it in a cache for later retrieval. So we can see on the second request for the same data, we go to the web server, and it communicates with the Redis server, and we get the data easily because it cached the data on the first request. As Elliot Spitzer once said, delay is the enemy of progress. So we really need to like speed up our application and be able to serve our customers in a matter of milliseconds. So what do we cache? What can we cache? We can cache sessions. So again, sessions identify the returning users, and we have already seen that the sessions can be stored in an external cache like Redis. But we can also store them in a permanent uh, like in a permanent storage, like for example a NoSQL database. The other thing we can cache is expensive responses. So responses that take too long to be processed and returned should be cached, because the first time it be processed, we need to store it in cache so that the second time the users need the results, we can just give the results back to the customers without having them to wait for the result. The third thing we can cache is frequently accessed data. So this same data which is needed every now and then by many users. So we should be aware of what data is really frequently accessed by the users. It's needed by the users, and we should store them in a cache. This will also like take away the load from our database. It will reduce the load our database is facing, and we'll be able to serve the customers really quickly. The fourth thing we can consider caching is the static content, which is the videos, images, the CSS files, the JavaScript files, and basically any other static content which is not changed every now and then can be cached. And as we'll see, we have a different kind of service to uh, to cache our static content. As with any other applications or any other uh, services out there, cache also has its own caveats, its own downsides, the things that you need to consider before using a cache. And one of the important things is that we need to make sure that we are not uh, our cache is not the data we are storing in cache is not updating frequently. So it's not like we are updating the data in a day like uh, uh, 30 times or something like that, because we'll then be serving our customers with the stale data, the data that's old. And we also need to know that it's not permanent. The cache is not for permanent storage. As we mentioned that Redis saves the data in RAM, which means the data is lost on restart. So we should consider, if we want to store permanently, we should consider using a PostgreSQL database or a MongoDB or something like on those lines. The third thing is that the eviction policy. So caches are quite expensive. We need to make sure that we are storing necessary data only. And how do we filter out the data? Like how do we know like okay, right now data A is being used frequently and data Z is not used at all. So how do we evict Z and how do we keep A? So we can use a policy like list recently used, which will evict the list, the items that the list used, and we can keep the data that is being used most frequently. Uh, this brings us to our next topic, content delivery network. So we had a look at the caching for serving customers with speed. In this topic, we'll be looking at how we'll be able to serve objects like the images, the videos, and the likes with speed. So we can make use of content delivery network. Uh, so today, it's available on AWS. It's available on GCP, and there is also another service, another service known as Cloudflare, which is most commonly used for CDN service. So what's a CDN? What's content delivery network? It's basically a cache for static contents. So as we mentioned, the static contents or the objects, images, videos, CSS, JavaScript files, HTML files as well. And what's unique about the CDN servers is that the CDN servers are placed in different parts of the world. So they are located in or at like different locations. So we can see in Africa we have them in America, in Russia, and like they're dispersed geographically. And the thing is that the users that will be near the CDN server, which will be near the users, will be able to serve the traffic faster. So, for example, if I have a server, if I have my server in Kenya and I want to be able to serve the people from the US, the distance is very long, and the distance, the physical distance actually matters. The farther away the servers are from customers, the expensive the expensive the response time will be, right? So with the CDN servers, we can actually have, if we have customers in the US, the CDN servers in the US will cache the static content, and they'll be able to get the content at a faster rate than getting the content from our actual servers itself. So how does CDN works? What's happening behind the scenes? Well, let's say that the first request a user sends to the it goes through the CDN server which is near the user itself. And the first time it's not the content is not in the CDN. It will the CDN will fetch from the original server itself, and it will take time. It will take, like, for example, it may take 120 milliseconds to serve the request. But then on the subsequent requests, the other servers which are near the same CDN server, they share the same CDN server, they'll be able to get the response at a much faster rate. So they might get the response at a 50 milliseconds time. The content, the actual content, the actual content that we are caching in the CDN may contain additional TTL header, which is TTL means time to live header, which will indicate how long it will remain in cache before being evicted. Considerations. So I believe there are two main things that you need to consider before using CDN service. And one of the thing is the time to live header, or the eviction policy, so to speak. So it's really important to consider setting a good TTL for the content, depending on how often it gets updated and how okay the company is to serve the stale content. You know, no, so there is no golden rule here. There's no one size fits all. Every company has its own need. We really need to consider talk with the with the company and see how we'll be able to set this eviction policy so that we update the content when it needs to, and at the same time uh, serving the customers at a higher speed. The second thing we need to consider is that we need to cache frequently accessed data. So we can't just cache everything we need, uh, even though it's not being updated every now and then. It costs money for the organization for using a CDN, and we should consider caching only the frequently accessed data to better our users' experience. So on one side we have the costs, and on the other side we have the user experience. So we should really look into the data that's being needed frequently and consider caching it. Coming on to our sixth topic, this is mainly on asynchronous and CPU heavy tasks. So we might have our servers running some uh, some services which are really heavy on CPU or are really eating up the resources. And some of these services can also be like runs asynchronously, behind, as the user does not have to wait on the web page to be able to like see the results. We can send a notification letter to the user and say, hey, your task is ready. So asynchronous tasks, these are the tasks that can be performed in the background without stopping the user from doing other things. And few of these are like sending out the emails. So for example, if you go to a website and you say, hey, I've forgotten my password, and you enter your email and you say, okay, send this to my email, it actually tells you that your email has been sent before actually sending in the email. So this is because to better experience as a user, so you don't have to wait staring at the screen like for 1 or 2 seconds, especially if you are sending out, if the website is sending out many emails. The other thing we can put in the background is processing images or videos. I will show you an example of this, and something else that you can put in the background is transactions. So when we are sending money, it's just like sending out emails. Just that we need to be careful with the transactions, so that if like we need to be really careful about the security concerns, and also like if we send out the money, I should not be able to. If even if I'm able to send out money once again asynchronously, the system should check if I have the sufficient funds or not before doing this second transaction. So let's look at like an example of this, and we have this compressed JPEG application over here on our web server. You can just search on Google like compressed JPEG, and this will be one of the first results. It can compress multiple things: JPEG, PNG, GIF, PDF format. And as you will see, when I upload a file over here, and let me select JPEG uh, file over here. Let me select a huge one, so that it takes time to actually minimize it. Uh, so yeah, this one, it's around 7.7 MB. Open it up, and as it is uploading, it's not stopping me from doing other things. So I can also go ahead and upload another file as it's uploading, you know, and I can do something. So it's not stopping me from using the website, and this is really like what's needed. And as it is compressing as well, I can still continue using the website. Uh, so this is the kind of experience we need for our users. CPU intensive tasks are tasks that consume lots of CPU power to do their job. And this kind of tasks will be separated out to their own servers, so that uh, we don't hurt our own application servers, and our application servers can do one thing, and this is to serve the traffic. So what are some of the examples of CPU intensive tasks? Well, some of them include machine learning models. So you might have some uh, models for application. Some data needs to be transformed, or you're doing some machine learning checks or anything which is consume high amount of CPU. It should be taken out. The second thing is processing images or videos. Again, as we saw in our JPEG compression, it's doing this thing. Uh, it's compressing our JPEGs or our PNGs, and it's actually doing it in other servers. So this server is free to serve us, and other users can use it as well without interruption. And then we have the data transformation. So this so when we want to like transform huge amounts of data, it consumes really uh, huge amount of CPUs resources, and also maybe RAM. So I mentioned that CPU intensive tasks might interfere with our application. And let's think of an example, right? So let's say we have this CPU intensive tasks which needs 60% of our CPU to do its thing. And we have our applications running on the same server, and they are running on and they're consuming at the moment like around 70% of the CPU is being consumed. And now when this process uh, gets started, it will start consuming like little by little, and it will reach like 50% of the CPU. And this is, as you can see, that we are now over consuming our server, and it will hurt everyone. It will hurt the process, the actual tasks, the one that's CPU intensive, and it would also hurt our end users, which are being served with basic, you know, uh, API requests. So how can we break decouple our application and allow like have them like communicate? How can we communicate our application server with those other servers which are doing the more heavy lifting stuff? So one of the things that we can make use of is message queues or pub subsystem, right? So this will allow us to decouple our application and allow the system to communicate and process operations asynchronously. It improves the performance, reliability, and scalability of our application. So we can have this pipeline over here. So we can have a message queue or pub sub, which means publisher and subscriber. So publisher means the one that's publishing to the queue, and the subscriber are the ones that are consuming from the queue. So it depending on what fits your needs, right? You want to make use of either message queue or pub sub and decouple your application, and have these worker servers to consume and process these tasks as they come in, right? So even these servers, you need to make them like more of scalable, so that we don't have tasks waiting in the queue for a longer period of time. Before we get started with QA, I would really like to comment something on the cloud itself, right? So as we have seen, we have all these different services, and like for example, we have the pub subsystem, we have this message queue, and it's really easy to set it up on the cloud today. I can go on cloud and I can have these different services in place. Cloud will also offer me a database server. Right? So we mentioned that I told you that I'll let you know later how we can have two database servers, and it's really easy with the cloud service providers today. We can go on GCP. We can have a PostgreSQL database, and we can, in a matter of click, like we can enable a high availability. So GCP will figure out that, hey, uh, the user needs high availability for this server, and it will actually replicate the data on another server. So, and it will be as a standby, or it will be acting as read replica, and it's that much easier to have a highly available. Like we don't have a single point of failure. Another thing is that, talking of fault tolerance, right? In system design, so fault tolerance is basically if our server goes down, the system can actually remove the server completely, create another one, and it starts serving the traffic. A new server starts serving the traffic in replace of the server that went down, and this is known as fault tolerance. So our the cloud is also made it very easy today to create this highly available, fault tolerant, and also to keep in mind the costs that we'll be having. Like we are only paying for what we are using and nothing more. So if my startup does not succeed, it's I can just delete the infrastructure I had and I can stop paying. That's it. That's the end of it. And one server, like I can have a one server, one minimal server at around $26 a month on GCP, which is really cheap. Uh, Not only that, but also like scalable. So as traffic grows, our servers can scale horizontally. And so, for example, if you go from one server to 5 servers or to 10 servers, we pay $260 per month, for 10 servers. But then if on first day we are using 10 servers to serve all the traffic, and then on the second day we only need 2 servers, GCP will do that automatically, and it will reduce the size of your cluster to 2 servers. So you will not need to pay $260. You just pay for those. It will calculate how long those 10 servers are up, and you'll only pay for the time they were up, and that's it. So I'll be now taking questions if anyone has any kind of questions related to the topic.
So I have one question. Which design considerations should you make in your application code to account for running in a replicated environment, in a highly available environment where do you need to think about, let's say, deadlocks or like read write consistency and things like that. Yeah.
Uh, so basically, we need to just have, if I got your question right, is that what we need to consider when making our application like highly available and uh, highly available, and also like in a fault tolerant environment, what we need to consider, right? So one of the main things that we mentioned is that we need to consider the state, the, the the state, right? The state of the application, the state of the data that we are storing in the servers. So we shouldn't be storing any kind of state, because fault tolerant means that the server will get evicted if it's not working, and it will be replaced. So if it's storing any kind of data in it, it will be wiped out. And also, like we mentioned, that if server one is storing your application, if your data and the requests are sent to server two, it wouldn't be having that data. So we need to like decouple out the architecture and store the data outside of the server. So this will make our applications run smoothly in an fault tolerant and highly available environment.
So we have a question from O. Are there any extra considerations to be made in the case of microservices?
In the case of microservices, yes, extra considerations. So we need to really look at how they'll be communicating, how the services will be communicating with one another, and also like as I didn't cover so many topics over here, like for example the containers and the Kubernetes, and really, if you are going with microservices, you will either go, you wouldn't be working with virtual machines. You will instead be containerizing your applications and running them on Kubernetes, or will be running them on a serverless architecture. So these are some of the things we have not covered over here. And another thing is that we need to have a gateway. We also need to have a gateway to be able to speak to our microservices, make sure like it's secure and everything related to it. So also another thing is that how we'll be handling the data in terms of microservices, because we really need to consider that how we'll break down the most important part is how we'll be breaking down the database to be shared or be consumed by the microservice. This data-driven architecture of microservices which we can look into. But I hope we'll consider looking at microservice in depth next time. Yeah.
Cool. There's another question from Uchacha on the YouTube live stream, asking about monitoring considerations that can be made or need to be made.
All right. So the monitoring consideration that we can we can use tools. So we already have so many tools at our disposal. So GCP offers this operation suite, which we can start collecting logs from all our servers into one place, into a single place, and we can also monitor the health of our cluster. You know, so how much CPU or RAM is being used at the total from all our uh, clusters, from all the servers in our clusters. The second thing we need to consider, if we are going with Docker and Kubernetes stuff, we can use tools like Prometheus and Grafana to be able to get the logs and the metrics from all these servers, from all the different servers running our application into a single uh, place where we will be able to view them and use Grafana as our dashboard to view them. Yeah.
Okay. Uh, does anyone else have any other questions? All right. Thank you so much for this workshop, Harry. It's been very informative. If we'd like to find you, where and if anyone would like to ask questions, or where can they reach out?
All right. Yeah. Thank you for having me. I hope this workshop was informative, and we all got to learn a lot. Uh, Also, not these are some of the questions you can be asked in our basic system design interview. Like if we are going for a software engineer role, we might get our DevOps role. We might get asked some of these questions like where do we place a cache, or how do we scale our system to accommodate users. So as an I hope this will help you in your interviews as well. So you can connect on LinkedIn. So my LinkedIn handle is Harith J, or you can find me if you type out Harith Bakhrani, you'll be able to find me on LinkedIn. And I also write articles on Medium, not very often, but every now and then. I've also written about system design, basically same stuff. It's also available in readable form. If you go to my handle harithj.medium.com, you'll be able to find this article and other interesting articles as well. Yeah, uh,
Awesome.
that's it
Thank
from
you
me.
and have a great day, everyone. Bye.
Bye bye.